Now let's talk about how to use a quarter wave transformer to match a complex load. ZL here is a complex load. It has both the real and the imaginary part. Same load we've been working with, so ZL is plotted here. If we want to use a quarter wave matching network, we know that L is going to be a quarter of a wavelength long. That's predefined. We also know that the impedance of the quarter wave transformer is going to be the square root of the characteristic impedances that are on either side of it. The characteristic impedance right here is Z0, so that's easy. But what is the impedance right here? That's the real part, and so let's call that ZR. And if we can find ZR, then we can find the characteristic impedance of the quarter wave transformer. So what we're going to do is take ZL and we're going to rotate a distance d towards the generator. See, here we're going to go towards the generator to the real axis. The place that the imaginary part is 0 is right along here. So we're going to rotate towards the generator until z reaches the real axis. And this distance right here is d. So d is going to be 0.25 minus 0.21 or 0.04 wavelengths. So we define that distance d, and then we need to read off the real part, ZR. So let's read the normalized value. ZR right here is about 2.65. And then we need to denormalize it, so we're going to multiply that by Z0. The value that I get is 132 ohms. So that's the ZR that I'm going to plug in right here with the Z0. Oops, I multiplied this by 50 and not 100, so there's a mistake. The value that I should have is 265 ohms, because this is 100 ohms and not 50. So plug that in, get the characteristic impedance of the quarter wave transformer, make it a quarter of a wavelength long, and you will have designed a quarter wave matching network for a complex load.